Hello guys, welcome back to my channel. Today I'll be doing an integral involving the fractional part function. So let's get to it. So we have the integral, let's call it I, equals the integral from 1 to infinity of the fractional part of x. Yes, it's fancy notation. Over x to the fourth dx. Now, you know, some of you might know how the fractional part function works, but for those who don't, I'll first need to explain how the floor function works. Say you have a number 2.1 and you take the floor of that, you get 2. And say you have a floor of 3.6, you get 3. So floor is basically the greatest integer less than whatever number you had inside, less than argument, you can say. So because negative 1.9 will give us a negative 2, not a negative 1, because negative 2 is the greatest integer that's less than negative 1.9. And fractional part is basically in some sense related to this. So say you have the fractional part of 2.1, you just get zero point 0.1. You have the fractional part of 3.6, you get a zero point 0.6. But if you have the fractional part of negative 1.9, you get zero point 0.1. So I mean, from all these connections, you probably have realized that the fractional part of, say, a number y is equal to y minus the floor of y. I mean, you can check for every case now. Well, 2.1 minus the floor of 2.1 is 0.1 when it correlates. Same with this thing. You can even check for this. You'll have a negative 1.9 minus of minus 2, which will give you a 0.1. So now we can write our original integral I as the integral from 1 to infinity of, instead of the fractional part, we can just say x minus the floor function of x all over x to the fourth power dx. Now we can totally separate this out to get the integral. We can separate this out into x over x to the fourth dx minus, evaluated from 1 to infinity, minus this integral from 1 to infinity, the floor of x over x to the fourth dx. Now over here we'll just obtain x to the negative 3, x to the negative third power dx. And for now we'll just write this as it is. We're going to be doing something unique with the second part. Well, we can just simply find the integral of this thing, the antiderivative. It's minus half x to the negative 2 power, evaluated from 1 to infinity, and minus 1 to infinity of this thing. Now when we substitute in infinity, everything just goes to 0 for infinity. So we'll have minus half and in bracket 0. When we substitute in 1, we'll just have a 1 minus this crazy integral over here. Now if you observe closely, this is nothing but a half minus this crazy integral. Now the only challenge here is to evaluate this thing properly. So I'm going to do that on another page. I'm going to include, I think, the negative sign too. I'm going to call it this thing I sub 1. Okay, we have I1 now. That's what we have to calculate. Now let's remember how the floor function worked. So say you have x that belongs to the interval. Well, let me include the starting number in 2 comma 3. So when x say is takes any value between the two, like a decimal value, say 2.3 for example. Well, the floor of x is always going to be 2. So over this interval, the floor of x is always 2. So why don't we make such partitions over here? So we have 1 to infinity, right? So why don't we make partition from 1 to 2, where we're including 1 and excluding 2. So unlike the first one, it's going to be closed 1 open 2, floor of x over x to the fourth. And then you're adding that with 2 to 3. Now you're including the 2 that we didn't include last time, and we're excluding 3. So this time it's going to be inclusive of 2 exclusive of 3, the same thing. And we are going to be doing this till infinity, right? So why don't we set up an infinite sum over here? I'll take the negative outside. The sum from say k equals 1 to infinity, because that's what our upper and lower bounds, our upper bound was, of, well, the integral of k to k plus 1 of floor of x over x to the fourth power dx. Forgot my dx here. Just write that in quickly. Well, on this, when we're integrating from k to k plus 1, so basically we are having k including k, excluding k plus 1. So, well, the excluding part, well, it just gets covered up in the limit definition of evaluating a definite integral. So I mean, on this interval, the floor of x is always going to equal k, right? Because that's the greatest integer that's less than our arbitrary x value in that interval. So we'll be left with sum from k equals 1 to infinity, integral from k to k plus 1. Instead of the floor of x, I can simply write k, k over x to the fourth power dx. I can just find the antiderivative now simply. Equals 1 to infinity. I can pull the k outside, and we're going to have a negative 3 here. And then we're going to have 1 over x to the third power evaluated from k plus 1 to k. Well, we can definitely plug in the upper and lower bounds now. Well, this negative and that negative becomes a positive. K equals 1 to infinity of why don't we write the 1 by 3 outside? 1/3, we have a k, and then when we plug everything in, we have a 1 over k plus 1, the whole thing cubed, minus 1 over k cubed. Now I would like to take the k inside, sum from k equals 1 to infinity of k over k plus 1, the whole thing cubed, minus 1/3 of the sum k 1 to infinity of k over k cubed. Well, now the problem is our denominator has this plus 1 associated with the k inside the power. So one way to make this a single uh, variable inside the power is by redefining the index. So instead of starting from 1, why don't we start from 2 to infinity? I mean, infinity plus 1 is still going to be infinity. We'll have k minus 1 over k cubed this time. I mean, I haven't changed the meaning. And here we have 1/3 infinite sum of 1 over k squared. I can split this up into few other sums now. K equals 2 to infinity of 1 over k squared minus 1/3 sum from k equals 2 to infinity of 1 over k cubed. Now the interesting thing to notice, wait, I have this part, I forgot about this. K equals 1 to infinity of 1 over k squared. Now the interesting thing to notice is this part is definitely the Riemann zeta function of 2. But we can again always get this to equal a Riemann zeta function only if we start our index k from 1. So in order to do that, we'll have to add and subtract the first term of our Riemann zeta series. What's the first term? Well, the first term when k equals 1 is 1, right? 1 over 1 squared is 1. So I'm going to add and subtract 1. So I have k equals 2 to infinity of 1 over k squared plus 1 minus 1. The same thing over here, sum from k equals 2 to infinity of 1 over k cubed plus 1, because again the first term is 1 over 1 cubed, which is 1, minus 1/3 the Riemann zeta of 2, right? Just by definition. And by virtue of this positive 1, I can rewrite this as sum from k equals 1 to infinity of 1 over k squared minus 1 minus 1/3 times the sum from k equals 1 to infinity of 1 over k cubed minus 1 minus, what's the Riemann zeta of 2? It's the pi squared by 6, right? You can definitely split this up because this is the Riemann zeta of 2 again, minus 1/3 minus 1/3. Now this is the Riemann zeta of 3. Lot of Riemann zetas here. plus 1/3 minus 1/3 times pi squared by 6. When this 1/3 are going to cancel off, and we're going to have 1/3 times pi squared by 6 here, and then I can just rewrite this term over here, minus 1/3 times pi squared over 6 minus 1/3 times the Riemann. I just keep messing up with the symbols. I'm so sorry, it's so weird. Zeta symbol, I never really understood how to, draw it completely. So, and the best part is everything cancels out. We are only left with negative 1/3 times the Riemann zeta of 3. Well, that is indeed our I sub 1, right? But what was I? If you remember, it was half plus our I sub 1. So we have half minus 1/3 times the Riemann zeta of 3. And this result, this fascinating result, is what we called Apéry's constant. So, beautiful result from this weird integral involving the fractional part function, and we had to go through an elaborate process of first understanding what the floor function is, then using this genius technique of having an infinite sum run from k equals 1 to infinity, and then changing the bounds of the integral. So it was essentially an integral whose limits, whose upper and lower limits were indices of these of were indices of this infinite sum. So it was like many linear integrals that are being added together successively. I mean, that's what we sought to do, right? When I said that, okay, like the floor function has a constant value over the interval of two successive integers, right? Like say 2 or 3, 1 and 2. Just called it k and k plus 1. Then made a sum run because our original bound was from 1 to infinity. So sum from k equals 1 to infinity, and then change the bounds of the integral according to the index of the infinite sum, and then just evaluate everything, because of changing this, the bounds of this integration, we could introduce a constant k instead of our floor of x. Then taking the constant outside, we could just do simple integration of x to the negative 4th power by using our power rules. Then plugging in the k value, then we just redefined the index because we had a k plus 1 cubed in the denominator. We wanted to make that one variable term. We want to make it like a cubed, b cubed, or like a single term. So by changing the index, making the index run from 2 to infinity, we could do some elaborate substitution and evaluation there. And then just playing along. Math is usually about playing along and following your intuitions, and hoping that they land you in the right direction. So eventually we cancel terms off, use the definition of the Riemann zeta function, and we ended up with this beautiful result, this Apéry's constant. So yeah, I guess that's it for this video, guys. If you like this video, please click the like button, share, subscribe. If you have any doubts, you can always reach me in the comment section. Have a great day, and I'll inform you about my next video. It's going to be really interesting. I have a lot of content now. So stay safe, stay home. Have a great day.